I'm Mr. McBrien. This is SCH4U, Introduction to Electrochemistry. So, just a quick snippet from the Ontario curriculum. We expect students to be able to analyze technologies and processes related to electrochemistry and their implications to various aspects of the Earth. And we want to be able to analyze these electrochemical reactions in various ways. So today we're going to talk about the principles of oxidation reduction reactions. Okay, there are lots of important chemical reactions involving the transfer of electrons from one species to another. What's interesting about that is the balanced equations don't show these electrons. And we won't understand them very well unless we can dig deeper and understand the electrical component of those reactions. We're going to refer to these typically as redox reactions. The reason for this will become clear in a few seconds. So what kind of reactions are we talking about here? In fact, most of the ones that matter. So corrosion is one, smelting metals, any kind of metallurgy, combustion, batteries, fuel cells, and lots more. Now, it's funny that we take the time to say this. They're electron transfer reactions. And if we want to talk about these intelligently, we have to keep in mind a very important truism. In electron transfer reactions, one entity will lose electrons and another entity, another compound, will gain those electrons. And it's critical that when we're looking at these reactions, we understand that the total number of electrons gained and lost is equal. So, we aren't necessarily going to see these electrons moving around. So if we take an illustration, we can take a solution of silver nitrate in a test tube, and we can insert a piece of copper. And after a little bit, something funny happens. Our clear colorless solution turns blue, and this gray furry stuff coats the copper. Now with a little investigation, we can figure out what's going on. Solid copper is reacting with silver nitrate to form solid silver, that's the gray stuff, and copper nitrate, the blue aqueous material. And even knowing that, it isn't quite clear that this is an electron transfer reaction. But that's what's going on. If we dig a bit deeper, the positively charged silver ions are accepting an electron from the copper to turn into elemental silver. And similarly, the uncharged copper is giving up electrons and going into aqueous form, into ionic form. But, once again, our overall reaction doesn't show these electrons at all. The electron transfer is hidden below the surface. So this rather busy slide talks about this in some detail. All right. And we want to just cover some basic definitions before we go any further. So a redox reaction is a reaction based on the transfer of electrons, and redox is just a way of short form for reduction oxidation. So what is a reduction in this context? Well, reduction is the gain of electrons from another substance. So a decrease in the charge of the species we're talking about. So that substance that is reduced is known as the oxidizing agent or oxidant. On the other hand, another substance will be oxidized. It loses electrons to the other substance. And this loss of electrons causes an increase in the charge on that species. And we talk about that species as the reducing agent. So overall then, we have a reduction process. Now in this illustration, we've got iron 3 positive accepting an electron to become iron 2 positive. A reduction in its charge. And in this illustration we've chosen for this purpose, copper goes from copper 1 plus to copper 2 plus and gives up an electron. It is oxidized. Overall, the electrons cancel, and we have iron 3 plus reacting with copper plus to form copper 2 plus and iron 2 plus. So iron is the oxidizing agent, copper is the reducing agent. Okay, and we will spend some time later talking about those two reactions as half-cell reactions. Each one is half of the overall reaction. And what's useful about those half reactions is those will include the electrons in their equation. The net reaction is what we observe at the macroscopic level, and we won't see electrons in that overall equation. So the net reaction does not have electrons shown explicitly. But we have to keep in mind, for a redox reaction to occur, both reduction of one compound and oxidation of another must take place. And the total number of electrons is constant. Okay, so if those electrons then are hidden, how do we understand what's going on? How do we track those electrons? Well, the answer is we use a trick called oxidation numbers. We use these to track electrons as they move on and off atoms. Okay, so let's talk about oxidation numbers. And these are also explicit, of course, in the Ontario curriculum. So oxidation numbers are a construct. They're bookkeeping devices that we use to track electrons as they move between species. We assign them to each individual atom, and they allow us to balance reactions and identify the elements that are actually changing. So, again, redox is a reduction-oxidation reaction. We should keep in mind the concept that the loss of electrons is oxidation, the gain of electrons is reduction. And in redox reactions, both occur. If you're having trouble remembering, the usual way that people look at it is loss of electrons. Leo says gain of electrons, GR. Leo says GR. Okay, so the oxidation number then is the number of electrons that are missing from an atom. If it's negative, the atom has actually gained electrons. So if we take magnesium as an example, it has an oxidation number. Magnesium 2 plus has lost 2 electrons. It has an oxidation number of +2. A chloride ion has an oxidation number of -1 because it's the charge on it. And these are trivial, rather easy. There'll be easy marks on the test. How do we determine the oxidation number of an atom that's part of a molecule, though? Well, we have to use a set of simple rules. And once we do this, it's just a matter of using our kindergarten mathematics. Okay, so elements have an oxidation number of 0. So whether they're in molecule form or whether they're in other forms such as iron solid, these have an oxidation number of 0. So we keep that in mind. Elemental form, oxidation number 0. Anytime we have monatomic ions, the oxidation number is the charge. So iron 2 plus, the oxidation number is +2. Chloride, oxidation number -1. Now in any compounds it forms with anything besides itself, fluorine will have a -1. Oxygen is usually -2, except in peroxides. And hydrogen is usually +1, except in metal hydrides. In those cases, hydrogen is -1. Okay, so what about all these other elements? Well, for the other ones, we're going to use kindergarten math to figure it out. So we're going to look at the species associated with a molecule, and I'll do some more examples, but I'll run through this one quickly. The species on the overall molecule, the charge on the overall molecule will give us the numbers if we use math associated with the ones we already know. Okay, so in this example, hydrogen's +1, oxygen's -2, but we have to keep in mind that oxygen, there are 4 oxygens there, so they contribute a total of -8. So we have -8 plus 1 is -7, but notice that the overall molecule is uncharged. So in order to balance that then, we have to have the oxidation number of chlorine in this case is +7. Maybe let's take a couple more, maybe simpler examples. So common table salt doesn't have a charge. We have to get oxidation numbers for it. Well, we've got a halogen there. So if it's not bonding with itself, it should accept an electron and become Cl negative. Once we know this, we can calculate the charge on sodium to get a 0 overall charge. So x plus -1 equals 0, x must equal +1. So another example, sulfur dioxide, such as is in pollution coming from various kinds of man-made activities. Remember, oxygen has a charge of -2, or an oxidation number of -2, except in peroxides. This isn't a peroxide. And remember that there are 2 oxygens here. So, -2 times 2 is -4, plus the oxidation number of sulfur equals 0. So that oxidation number must be +4. Alright, but sulfur can have a lot of different oxidation numbers. So let's take sulfur trioxide, a major component of acid rain. In this case, again, oxygen with -2, but now there are 3 of them. So we have a total contribution of -6 from oxygen. Again, the molecule is uncharged. This means sulfur has to have +6. One more example, we'll belabor the point a little bit. Elemental magnesium reacting with sulfur to form magnesium sulfide. What are the oxidation numbers? Well, in this case, if we examine the periodic table, we can see that magnesium metal is liable to form a +2 ion. It has 2 valence electrons that it wants to lose. So from that we can get sulfur at -2 to get its full octet. And remember, of course, that in elemental form each of these has an oxidation number of 0. So there's our overall oxidation states of each one. So once we do know, and that was a little hint towards where we're getting to next, once we know the oxidation numbers, we can, if we know them on both sides of the reaction, we can then decide what's being oxidized and what's being reduced. And so if we look at our magnesium sulfide example, our 2 valence electrons for magnesium are taken by the sulfide, And there's our overall Lewis visualization of what's going on. If we look at the overall reaction, we can see that magnesium went from a charge of 0 to a charge of 2 plus. Sulfur went from a charge of 0 to a charge of 2 minus, or an oxidation number of 2 minus. Well, loss of 2 electrons is oxidation, gain of 2 electrons is reduction. So we've identified which component is oxidized, magnesium, and which one's reduced, sulfur. So some real-life examples. We can look at how nickel is produced from nickel ore, from nickel 2 oxide. So up in Sudbury, they'll react nickel oxide with carbon. And this is the overall reaction here to get pure nickel and produce carbon monoxide. So we know oxygen is a -2. That puts nickel at +2. Elemental carbon has a 0. Elemental nickel is a 0. Oxygen again at -2, and carbon monoxide gives carbon a +2 on the right-hand side. So now we can identify which is being oxidized, carbon in this case, because the oxidation number is going up from 0 to 2. And which one's being reduced? Nickel is being reduced from 2 to 0. So let's take a different kind of example, combustion. So the space shuttle burns hydrogen in order to, or used to burn hydrogen as fuel. Liquid hydrogen reacting with liquid oxygen to form water. Again, we have elemental form for both of these guys, so they're going to have an oxidation number of 0. On the other side, hydrogen is a +1, oxygen -2. Excuse me. It doesn't matter that the bonds that we form in water are covalent bonds and that the electrons are partially transferred. This has no impact to our basic idea of how oxidation numbers work. So remember, we've already talked about this concept. The substance that gains electrons is the oxidizing agent. The substance that loses electrons is the reducing agent. So in this case, oxygen is is gaining electrons. It's the oxidizing agent. Hydrogen is losing electrons. It's the reducing agent. Okay, so to conclude then, we have lots of important reactions to think about that involve the movement of electrons between reactants. We call these redox reactions. In order to understand them, we have to track the electrons over the course of these changes, and we do this by assigning oxidation numbers to the species involved. So for homework, please read over the note and have a look at the oxidation number worksheet. You should be able to work through most of those today. Thank you very much. Have a good night.